is this particular Thomas Fermi problem that I'm going to discuss, is it well posed? Does it A, have a solution, and B, have one and only one solution? They're the two questions we're going to discover and work on. That's the core of the research today. Now, you may have already heard of Thomas Fermi. So it's named after two famous physicists and applied mathematicians called Thomas and Fermi. So let me just share my screen with you, give you some pictures. Here is Thomas, and here is Fermi, just taken from Wikipedia, these two pictures. Okay, so let's get down to business. Oh, by the way, this presentation is the basis of a new research paper of mine and Mark Holzer's that will appear in the journal Differential Equations and Applications. Now, this is an open access journal, so I will put a link in the description of the YouTube video and you can download it and see the full discussion for free. Okay, so let's get down to business. Okay, so let's get down to it. Now, the type of problem we're going to look at is known as a boundary value problem. Okay, you have a differential equation. In this case, it's a second order nonlinear differential equation on this interval. X naught is some positive value. And you have what's known as boundary conditions. At the left-hand endpoint of this interval, the boundary condition is 1, and at the right-hand endpoint, it's 0. Okay, this kind of problem is known as a Thomas Fermi problem associated with the heavy atoms in intense magnetic fields. Okay, it's non-linear, and I'm not going to derive it, but you can find the derivation of the problem found in the paper. Now, the derivation is probably a video in itself, so I just really essentially wanted to talk about the new results in this presentation. All right, now, you might be asking, what are y and x here? Well, x is the independent variable, y is the dependent variable, so y is a function of x, and they're both non-dimensionalized variables associated with the problem under consideration. Okay, so what are we going to do in this video? Well, I'm glad you asked. We're going to do 3 things. Let me share them with you. We are going to show that this problem has at most one solution. That means there's either no solution or one solution. Then we'll go further and show the problem has at least one solution. So combining point 1 and point 2, you get a unique solution to the problem. You know that one exists. And thirdly, we will provide a location for the solution, some bounds or some geometric insight into where the solution lies. Now, why would you want to answer these questions? They are very, very deep questions. Well, like I said at the start of the video, a smaller title for this presentation is this particular Thomas Fermi problem well posed? A well posed problem has a solution, and it has only one solution. Okay, these are basic building blocks to advance the theory of any kind of, say, differential equation. Okay, so let's have a look at our main theorems then. So we'll come back to this in a minute. Okay, this is the main, or the first theorem. I'm going to present 2 theorems to you. Okay, so all right. So the problem that we're looking at, let's say x naught is positive for arbitrary but finite positive x naught. The BVP, or boundary value problem, 1 through 3, has at most one solution on this interval. So just once again, this means that the problem has either one solution or no solution at all. Okay. All right, so how do we prove that? Well, basically, the proof involves exploiting the monotonicity of the right-hand side of the differential equation in the y variable. Okay, this is an increasing function in the y variable. Okay, so let's actually just go through that. Okay, so it is a very common type of proof in mathematics for these kinds of these kinds of theorems where you want to show that there's at most one solution. This is a non-multiplicity solution. So what we're going to do is we're going to let u and v be two solutions. So they're functions of x and they both satisfy this problem here. Okay. What we're going to do is show that if there are two solutions, then they are identical on the interval. That means that they are one and the same solution. So any two solutions must be identical. Okay. All right. So that means there is at most one solution. Okay. All right. So how do we do it? Well, let's let R be this difference here between the two functions, u and v. And because u and v are solutions to this problem, they have to be, twice differentiable, and their second derivatives have to be continuous. So both u and v have to be continuous functions. So R must be continuous. Now, since R is continuous on a closed and bounded interval, it must achieve its maximum and minimum values somewhere in the interval. Okay. That is a basic property of continuous functions. Every continuous function on a compact interval must achieve its maximum and minimum values. Okay, so let's let x1 be the point that we know exists from the previous sentence, be such that R has its maximum value on the interval at x1, right? And we know that it's and we'll argue by contradiction in the sense that we'll assume that it's a positive maximum. Okay, so let's assume there that u of x1 is strictly greater than v of x1. Now we'll actually show. Oh, hang on, my camera has just died. Hang on, let me just go back to that. Just bear with me for a second. Okay, we're back. Sorry about that. Just had to restart my document camera. Okay, so let x0 be the point in this interval, which we know exists. That R1 has its maximum value, and let's assume that the value of R at x1 is positive. Okay, let me just share my screen with you again. Okay, so let x1 be the point in this interval be such that R of x1 is the maximum value and it's positive. That is, u of x1 is greater than v of x1. What we're going to do is show that this cannot hold. Okay, we're going to reach some contradiction to this somehow. Okay, all right. So how do we do that? Well, let's go through. We'll show that this can't hold. We'll show that this x1 cannot be the point at the endpoints of the interval, so it can't be 0 or x1. And we'll also show that x1 can't actually be in the interior of this interval. So we're going to rule all the points out. All right. So let's say that x1 equals 0. Then this boundary condition, if you so this would be basically it would be 1 minus 1 here, which will be 0. That definitely means that this can't be positive, right? So we can't have x1 equaling 0. And similarly, if you look at the other boundary condition, you'll have 0 minus 0, which is 0, which cannot be positive. So it cannot hold for x1 equals x0. So what does it mean? x1 cannot be at the endpoints of the interval. Okay, what about in the interior? What about between x0 and x0? All right, well, we rely on a basic maximum principle. If this is the maximum value and it happens to be in the interior of this interval, then what do we know from basic calculus? You know that the derivative is 0 at that point, and the second derivative is less than or equal to 0. That is a basic maximum principle. Okay, so what does this mean? Well, let's go back to 4. Let's differentiate this once and twice, and we get this. And now remember, u and v are both solutions to this problem. So we can replace u double prime and v double prime with this square root. So what does that mean? Well, you get this. And we know that u of x1 and v of x1 are related in the following assumption. V of x1 is greater than u of x1. So this has to be greater than this. So this is positive. So we get r double prime of x1 is greater than 0. But hang on, that contradicts this. So how can the second derivative be positive and non-negative? Okay. Well, the answer is it can't. We've got the contradiction that we wanted. So let's go back, and what we initially assumed mustn't be true. So essentially this cannot be true, right? But what we're trying to do is show this. We've shown that this can't be true. So what does it mean? It means that on the entire interval, u must be less than or equal to v. In other words, u must be less than or equal to v. Okay, so that's that's a step in the right direction towards that. Okay, we reach contradiction, and so this cannot hold. So you combine all the cases, and you get this inequality. All right, so now what you can do is repeat the process and show that r is greater than or equal to 0. Okay, so basically you repeat the argument and show that r is greater than or equal to 0 in a similar contradictory style to what I showed you before. Okay, so if you go through and do that, I'll leave that for you to do. I'm not going to repeat it. It's very, very similar. So you've shown that r is less than or equal to 0, greater than or equal to 0. So what does that mean? It means that r has to be identically equal to 0, of course. Okay, so you get this. So what does that mean? There is at most one solution to our problem. Okay, so our Thomas Fermi problem has at most one solution. Okay. Again, that just means there's either no solution at all, or there is a unique solution. There's one and only one solution. So which one of it is it? Is there no solution, or is there one and only one solution? Well, the next theorem helps us work that out. So let me share that with you. Okay, the second and final theorem that I'm going to share with you. For arbitrary but finite positive x0, the boundary value problem, the Thomas Fermi boundary value problem that we've been talking about, has a unique solution, which is twice differentiable and has a second order derivative that's continuous, such that the solution lies between this function and this function on the interval. Okay, so let me just box that up for you, because this now answers the question about existence of solutions. Okay, so let me just draw a little picture before I get down to the proof. So what does this mean? Well, it means that the solution, let's say that's 1 and that's x0. Okay, the solution lies between this function and this function. So it might look something like this. Okay. All right, so this little triangle is the sort of the set, I guess, that contains the solution to our Thomas Fermi problem. Okay, so that's the location of the solution. That's the location of the solution. All right, let's get on with the proof then. Let's get on with the proof. So all we need to do in this proof is to show that the original Thomas Fermi problem has at least one solution. And then we combine that with theorem 1. We know, okay, well, there's at most one solution and at least one solution. It means there's one and only one solution. Okay, let's get down to it. All right, so what we do is we modify this right-hand side of this differential equation, and you modify it in such a way that the right-hand side is continuous and bounded, uniformly bounded everywhere. Okay, now this is a common technique in the theory of boundary value problems. And then what you do is you consider the modified problem and you show that there's a solution, and then you use differential inequalities to show that the solution to the modified problem is really a solution to the original problem. Okay, let's get down to that. Okay, so I'm not going to talk about this too much. The idea uses an idea called Schauder's fixed point theorem, and I'm actually going to take a simpler method, a simpler approach there. Okay, in the paper I do a full-blown proof of that. In this presentation, just to save a bit of time, I'm going to use a result due to a mathematician called Scorza-Dragoni from the 1930s, which simplifies things even more. Okay. Okay. All right, so here is the modified differential equation that I'm talking about, and it is a real monster. It's a beast. Okay, we've got this new right-hand side, G, which is defined in the following way. Okay, it's defined one way for everything sort of outside here. It's defined another way for everything down here. And it's just a regular problem for everything inside this triangle. Okay. Now this is a beast, but they're you know, you can see this is related back to here. So this appears sort of here and here and here. Okay. Okay. So this function is continuous everywhere and it is uniformly bounded. Okay, and this is really important because this simple result of Scorza-Dragoni may be applied. Like I said, the full proof using Schauder's theorem is in the paper. Okay, so what it means is that the differential equation y double prime equals g, subject to the original boundary conditions, has a solution, has at least one solution. Okay, so this differential equation coupled with these boundary conditions has at least one solution. And now the challenge is to show that the solutions to this problem with the boundary conditions from the start actually lies in this region, and therefore that's where the equation's unmodified. So the two boundary value problems are the same. Okay, let me say that again. We've shown that this special modified boundary value problem has at least one solution. Okay, just using this Scorza-Dragoni result. The challenge now is to show that the solution, that there's at least one solution that lies in the place where G or where F is unmodified. Okay, that's where G and F are identical. Okay, so that's what we're going to try to do now. Okay, we want to show that solutions lie in here because that and our F are the same function. Okay, so what we're going to do is show that Y is less than or equal to this. So what we're going to do is show that the solution to the modified problem stays below this straight line here. Okay, now I won't show the case that shows the solutions, there's a solution that is greater than or equal to 0 because it's very, very similar. Now, the idea that we use again is a maximum principle, just like the proof of theorem 1, combined with some contradiction, proof by contradiction arguments. Okay, so this is what we're trying to do. How do we do it? Well, again, you'll notice a pattern now. Let W be the difference between these two functions. Again, this is a continuous function. This is a linear function, a straight line, so it's continuous. The W must achieve its maximum value on this closed and bounded interval. Okay, so let's let x2 be the point, which we know exists, be the point in this interval, be such that W has a positive maximum on the interval at that point. That means we are assuming that this x2 is such that this holds. So we're sort of arguing by contradiction here. We're assuming, we're saying that this doesn't hold for some x2 point, which is the maximum value and is a positive value of W. So we'll show that we reach a contradiction. All right, and again, similar to the proof of theorem 1, if you look at the boundary conditions, the x2 point cannot be the left-hand endpoint of the interval or the right-hand endpoint of the interval. Okay? So now, if x2 lies in the interior, we know from the basic maximum principle that the derivative is 0 at x2 and the second derivative is less than or equal to 0. Okay, so what we're going to do now is take this, differentiate both sides twice, that'll disappear, and evaluate it at x2. So we get this equals this, because the linear part has, or the line part has disappeared. Now remember, y is a solution, so we can replace y double prime with g, where g is the modified function. And it's this thing because we've assumed that this is the case. So in the modified solution, this is the case here. This is the crazy function here. So that's it at x2. And what do we know about this? Well, this is positive by assumption, this is positive, and this is positive. So the whole thing's positive. So we get W double prime at x2 is positive, but we know that W double prime at x2 is not positive. So it is another contradiction, similar to the ideas in the proof of theorem 1. So we reach contradiction. So x2 can't be the left-hand endpoint, the right-hand endpoint, or occur in the interior. So what do we know? We know that the initial assumption that we made must be incorrect. So this cannot hold. So what's the opposite of this? Well, it means that this must hold on the entire interval. Okay? So in a similar fashion, you can show that y is greater than or equal to 0 on this whole interval. And what that means is that solutions to the problem satisfy this, and G and F are identical here. So there must be at least one solution to the unmodified problem. Theorem 1 says that the problem has at most one solution. Theorem 2, so far, the proof says the problem has at least one solution. Put them together, you got uniqueness. You know that there's one and only one solution to the Thomas Fermi problem. And that is the last line in here. Okay, so we're really happy because the original problem is once and for all shown to be well posed. The Thomas Fermi problem here has one and only one solution. Okay, so why is this kind of result important? Well, I'm glad you asked. This is a basic but important thing to know, because when you have models for physical or dynamic phenomena, a first question is my problem well posed? And what does that mean for, say, a differential equation? It means you ask questions. Is there a solution? Is there one and only one solution? Without this kind of information, it's very difficult to get to the next steps with any reliability. So what I've done today is really shown you some of the bedrock theory that Mark Holzer and myself have created for this problem. Anyway, hope you enjoyed it. I hope the mathematics wasn't too crazy for you. I've tried to keep it as simple as I can, and like I said, it's designed for someone who's done a second course in calculus, something like that. Anyway, hope you enjoyed it. If you have any questions, any comments, leave them in the comment section, and when the paper's ready at the journal, I will post a link in the description. Thanks for watching, everybody. Bye.